All right, so let's try to be semi-productive here. I've been recording a lot of videos that I haven't put up yet with basically just me yelling at clouds. So what I want to talk about today, is a video I promised people in my group, is about the idea of supercompensation and why, well, A, why it's wrong, but B, why it's a poor model for the training process. And I'm going to talk about some other stuff related to that, like the General Adaptation Syndrome and a lot of things that get applied to training that are simply incorrect. A lot of what I'm going to talk about are ideas I saw presented in a new paper. It's by Buckner et al., The Basics of Training for Muscle Size and Strength. A brief review on the theory, Medicine, Science, Sports, and Exercise, 2019, October, EPUB ahead of print. I do want to mention one of the researchers on this, guy named Jeremy Loenneke. He comes out of a lab that does seem to have a fairly high-intensity training, HIT bias, based on their paper. He has also, in my opinion, laughably said that that getting bigger muscles doesn't increase your strength and that powerlifters who have hypertrophy phases are wasting their time. And, well, let's just say that. I don't agree with that. Regardless, and I'm not using this to dismiss the paper, realize that this is kind of the direction they're coming from. They still make good points. They cite their references. I agree with more of what they write than not, based on what the other literature says. And I'll link to other papers, both in the description and in the article. So first, what is supercompensation, right? The idea of supercompensation in training is that you train, and for some brief period of time, your performance is decreased, or some aspect of performance, or in some cases, some substrate is depleted, at which point, over time, as you recover, it rebounds to a higher level, right? So in the context of strength, the idea would be, okay, you go and you train your ass off, and if you were to test your strength the next day, you would possibly be weaker, and then a couple days later, you would supercompensate and you're stronger. And the same thing gets applied to muscle growth, right? And I mentioned this at some point recently. Oh, in my tension series. Right, one of the longest standing theories of growth is that when you train, you break down muscle tissue. So presumably you now have less than you started with. And then as you recover, you supercompensate to a larger muscle. And simply, it's wrong. It's just really that easy. Now, at least in an overall picture. By that, I mean that in a sense, it does describe what's happening in terms of your performance, in a sense. Although in many cases it doesn't, right? In many cases athletes will train daily, and it's not as if the performance ever decreases. And when I address another model, you'll see that they are superficially similar, but have very different implications. Predominantly, my dislike of the supercompensation theory is the original research that it's based on. And it's interesting in looking at where this idea came from. And you can track it back to a Russian researcher in the 50s. I'm going to pronounce his name Yavorek. I've seen it written as I-A-V-O-R-E-K, and I think that's a Cyrillic to American alphabet issue. So I'm going to say Yavorek because I suspect that I would be a J transliterated. I could be wrong. And what he was studying was liver glycogen in rats. And what he found was that if you deplete liver glycogen and then refeed them carbs, it goes to a higher level. It supercompensates. And an entire theory of training was born. Now, liver and muscle glycogen are two places where you can get supercompensation, right? They've been doing that since, I want to say, the 60s, right? You carb deplete with a combination of high volume training and a low carbohydrate diet. You deplete your muscle glycogen, and then when you refeed carbs, you supercompensate to whatever, 110% or 120% or whatever, where you started. So in some cases, there can be supercompensation, mainly glycogen. Certainly over time with training, things like muscle creatine phosphate can increase, but that's not really, it's not a depletion and an increase. The problem with applying this is twofold. One is we are dealing with one specific substrate. Two, the theory of supercompensation would be that you train, your performance is lower, you supercompensate to a higher level. You train, your performance is lower, you supercompensate to an even higher level. You train, performance is lower, higher, you stair step up. That doesn't happen with glycogen. You can do it once. And if you were to completely deplete and reload, it'll go right back to where it was. There is no continuous increase. So maybe you go from 100 to 125%, but you never get to 135 and 145. So it doesn't apply to anything else. It doesn't even apply here because you can't, the idea that you can stair step to higher and higher and higher levels doesn't happen in muscle or liver. But if you only look at it once, you get this false idea. And so that was basically where that came from. And it's not correct. Because that, now some people go, oh, but you know, after you train hard, you're weaker the next day. And that's true. But it's not in a supercompensation model. And that brings me to the better model we have called the fitness fatigue theory of training, which some of you may have seen, and the graphic is up here. The idea behind fitness fatigue is a little more nuanced. The idea is that training improves your fitness by some amount, but also increases your fatigue by some amount, right? And the idea is that the difference between the increase in fitness and the increase in fatigue represents your performance. And that you can see this on the graphic. The original theory, which is very mathematically based and has been shown to be actually more or less correct, it was a good theory being, from what I can tell, kind of pulled out of nowhere, was that during the recovery process, fitness takes 3 times as long to dissipate as fatigue. Right? Does that make sense? So let's say you train and you improve your fitness by 5%, but you increase your fatigue by 10%. If I were to remeasure you the next day, your performance will be down by 5%. Right? 5% up minus 10% is negative 5%. If we wait several days, fatigue will dissipate, but fitness will be maintained. And then at some later date, we will see that fitness realized. We'll be able to measure it and you will be stronger. And that's actually sort of the idea behind tapering and deloading, right? You frequently see this rebound in performance because now this wouldn't work. If fitness and fatigue went away at similar rates, this wouldn't work because you would just be spinning your wheels and pissing into the wind. But because fitness takes longer than fatigue to go away, we can get this performance improvement over time. This is also how things like maintenance loading, right? If I've been loading you with 8 heavy sets twice a week and generating some amount of fitness and some amount of fatigue, and I cut your training volume while maintaining your intensity, your fitness will be maintained or may increase while the fatigue dissipates. That's how tapering works. Now, if you put the curves next to one another, the supercompensation curve and the fitness fatigue curve, they look superficially very similar, but they are saying completely different things. Supercompensation says that you first deplete something, less glycogen, less ATP, less muscle, less mitochondria, which then overshoots to a higher level. Fitness fatigue is saying nothing of the sort. Fitness fatigue is not saying you're depleting anything. You are generating some amount of fitness and some amount of fatigue, and as fatigue. So again, the curves look very similar. And now I've actually got a haircut. One thing in terms of fitness and fatigue is that it's really descriptive. So far as I can tell, no one has tried to tie the fitness or fatigue components to a biological characteristic within any tissue. Now, I could be wrong. I haven't really kept up with it of late, right? Like, I don't think it's just like, oh, fitness is an increase in this and fatigue is an increase in something else. I think it's just more of a descriptive concept, I think. Like, I actually, for over a decade, like, I've thought about, okay, what would be the biological determinant of fatigue? Right, it could be neurological, either peripheral fatigue or central fatigue, which does exist, contrary to the belief of some zealots who should stick with statistics. In a muscle growth sense, I don't know, myostatin, but I don't know if it's really just more of a descriptive how preparedness is being impacted by these fitness and fatigue components. Whereas supercompensation, yes, it is a time course, but at least it was based initially on the idea of this biological rebuilding of a depleted substrate. And that's just not how it works. And I guess as an example of fitness fatigue, we might look at the idea of post-activation potential. right? The idea of that is that we do like a heavy triple or an explosive jump or something before 1RM. And by dialing up the nervous system and whatever, you get a higher performance than you would. The thing is, when you look at the studies, what you see is that more advanced athletes get an improvement and less advanced athletes tend to get a decrease. This is because that heavy triple is generating some improvement in fitness and some improvement in fatigue, amount of fatigue. Whether or not you see an improvement acutely depends on which goes up higher and which goes away faster. In advanced trainees, you get a bigger boost of fitness and less of an increase in fatigue. In lower trained, you get less increase in fitness and a greater increase in fatigue, right? So to that, I'd add there's also a time issue, mainly to do with the rest interval, right? So you've done your potentiation activity, whatever it is, power cleans or heavy triple in the squat, whatever. And if you were to go immediately or a minute later, you would probably see performance decreased, no matter what your training status was, because the increase in fitness has been outweighed by the increase in fatigue. So acute performance is down. Now, if you wait till the 3 or the 5, or I think in some cases even 7 minutes, performance goes up because fitness is being, the acute increase in fitness is being maintained while fatigue is dissipating, which ties into what I said earlier, right? This only works because fatigue, whatever it is, dissipates faster than fitness. But in a post-activation, and PAP is just like an overall model of this. Both the increase in each determining your preparedness, but the fact that the different time courses allow you to get an increase in fitness as fatigue dissipates faster. So in addition to the conceptual differences between supercompensation and fitness and fatigue, like I said, they look superficially very similar. However, they have enormously different implications for how we train. Right? Supercompensation says you train, you get a little bit weaker, smaller, slower, you wait till you see supercompensation, and that's the ideal time to train. It's a full recovery model. It says you do not train again until you have supercompensated to a higher level of performance. And anyone listening to this who's not a ranked beginner knows that that is ridiculous. Right? Imagine a top sprinter, powerlifter, Olympic lifter, lifting and then going, I'm not going to train again until I can put more weight on the bar. That's the HIT, the high intensity training fallacy. Doesn't work. Whereas the fitness fatigue implication says you can accumulate training, right? We know people Olympic lifters who train 5 days a week. Now they may be varying intensity. They may not be, depending on what approach to training they take. But they are not waiting for supercompensation to occur because it doesn't. They are accumulating some amount of fitness and some amount of fatigue. And eventually, maybe when they taper, maybe not, their measured performance will improve, right? It may take in a high-level powerlifter, Olympic lifter, 12 to 16 weeks to add 5 pounds in a lift. What are they supposed to do? Train once and then train again 16 weeks later? The supercompensation idea, even if it superficially describes training, doesn't make any sense in terms of what it implies from the training process. Right? Now, a beginner to look like that, right? A beginner will train on Monday and be a little stronger on Wednesday, be a little stronger on, supercompensation, but it's really not. What it is that they are generating fitness and fatigue at low levels, and fatigue is going away very quickly. At higher levels, you have to overlap training, right? Swimmers will swim 10 times a week or 12 times a week and whatever, and they may be very tired, and some days performance is down and some days it's not. But what they are doing is they have to train frequently enough to generate enough fitness for it to matter. Because if they waited based on supercompensation, which is I'm going to train every other day, their training load would be so low it wouldn't stimulate fitness. So the fitness fatigue model describes things much better. I mean, I guess the closest we have to maybe supercompensation is something like, those double shock microcycles, or Westside does, the Circamax, where they just murder themselves for 3 weeks and then taper out. And yeah, in those cases, you do see a decrease in performance and it looks like supercompensation, but it's not. You are generating an enormous amount of fitness, an enormous amount of fatigue, and then hoping that the fatigue dissipates in time. The supercompensation, what comes out of it practically for training just doesn't work and doesn't make any sense. So supercompensation as a general concept is simply wrong. It tentatively applies for something like muscle liver glycogen, but even they don't keep supercompensating up and up and up. They do it once. The whole model is incorrect. Now that brings me to a secondary part of this, the General Adaptation Syndrome, and how it has been misapplied to training. Because it is often used to not only support some of these training ideas, but also global periodization. And the paper I cited was looking at periodization more than anything, and whether or not it has any validity, or more importantly, whether it can be based on the General Adaptation Syndrome. Right, so history. Hans Selye was I think lab intern actually, way back in the day, like early 20th century. And while he is given great credit for his discovery, as Robert Sapolsky once put it, his main claim to fame is that he was incompetent at handling lab rats. Because what they were trying to do was study lab rats, and basically he was bad at it. He couldn't keep a hold of them, so he would drop them. He would chase them around the lab. He would basically expose them to all this kinds of stress. And then he did some measurements, and he found, wait, holy shit, they're having this stress response that they were getting because he sucked at his job, right? And this led him to do these experiments where he exposed them to lots of generalized stressors: heat, cold, noxious poisons. If it had existed, he would have put Justin Bieber on loop, right? And what he found was that these animals showed a generalized stress response, right? Because at the time, everyone thought heat is heat, cold is cold, being sick is being sick, mental stress is mental stress. Each one, the disease model of medicine was a given disease has a given set of symptoms. What he said was, no, there's a general stress symptom. And he also found other things. Cortisol was elevated, the adrenal gland shrank due to the stress. There's all this stuff going on. And everyone said, no way, man, no way can there be a generalized response to so many diverse stressors. And it turned out he was right. And the model he came up with, the General Adaptation Syndrome, was that when you were, and I'll put up the graphic of this too, when you're exposed to stress, you go through 3 phases. Alarm, which is sort of the initial stress response, right? You go train hard, you get stress hormones, cortisol, adrenaline, noradrenaline, all these hormonal changes, right? That is the alarm stage. Then you get what's called the resistance stage, right? In an animal sense, it is their ability to tolerate the stressor, right? Now, in modern times, we call this, it's the idea of allostasis. It's the idea of total allostatic load and your ability to resist it. There's also other shit going on. Talk about it in the women's book, actually, huge chapter on stress. So there's the resistance phase where you are adapting and handling the stress. And then with chronic stress, there is the exhaustion phase. And this is when the system shuts down. Right? So, because it can no longer adapt to the chronic stress. And make no mistake, we know that chronic stress causes all sorts of problems. I will always recommend the book Why Zebras Don't Get Ulcers by Robert Sapolsky. Best book on stress you'll ever read. He's who I want to be when I grow up with less crazy hair. Although I'm getting there. So that got applied to training, right? So let's think about this. Okay, we expose an athlete to a stressor. That's the alarm. Assuming the training load is sufficient, we enter the resistance phase, and they adapt. But if we expose them to too much stress acutely or too much stress over time, they overtrain or overreach, and they enter exhaustion. It seemed logical. It made sense. And superficially, the curves actually look very similar. Right, if you continue, it's a little different the way I've presented it, but if you just kind of continued that involution, because you were training and training and training, performance would go down. And the curves actually look pretty similar. And that got used to base periodization schemes. We're doing high volume into lower, we're going to use high volumes until they start to blow up, and then we're going to taper them or reduce their volume so they don't fall into exhaustion and they supercompensate. Supercompensation being incorrect anyway. And that was the model for years. Like Mike Stone put that out in the 70s or 80s as a theoretical model of periodization. But it's not a good model. And I want to read you a couple of quotes from this Buckner et al. Paper. This is probably my favorite. Selye himself referred to the gas as a syndrome that appears when severe injury is inflicted upon the organism. Indeed, it has been questioned whether lethal and graded doses of different agents can truly provide insight into the physiological adaptations that would occur with non-toxic levels or doses of resistance exercise. For example, in Selye's original model, the exhaustion phase was represented by death of the organism, right? It wasn't fatigue, exhaustion in the sense we typically use it, death. Which admittedly, if you're training your athletes to death, Well, that's hardcore. They don't tend to taper well, in my experience. So they're basically saying that the gas as Celia presented it is really not applicable because the exhaustion stage represents something very, very different. And it's also basically exposure to toxic agents. To that, I'd add that the end result in Celia's work is not the same as what happens in Okay, it gets way more complicated than this. Read the woman's book. So in Celia's model, when he measured, right, the system had just shut down. The adrenal gland was shrunken. Presumably, I mean, it's hard to say, and people will go, oh, adrenal exhaustion. Well, number one, adrenal exhaustion is not a thing. Number two, what you see in humans is that with chronic stress, cortisol goes up and up and up. And then, yes, the system does kind of shut down, and you get this pseudo disease state where they can't produce enough cortisol. But it's not adrenal fatigue. It's not depletion of anything. It's not anything you've ever heard about. It's an adaptation in the system to try to prevent more damage. But basically, the end result in Celia's animals and the end result in overtrained humans are not the same. If for no other reason that the humans aren't dead. Well, they shouldn't be. The next bit is really kind of what I think is important. Within the field of molecular exercise physiology. Now, okay, let me back up. Make no sense. Based on what we know about training then, right, I don't like to judge stuff from 40 years ago based on what we know now, because that's not fair, right? They were basing these ideas on the best knowledge of the day. The problem is now we know better, and we shouldn't be using these inaccurate models. They add, within the field of molecular exercise physiology, it has been suggested that the gas and its resulting supercompensation hypothesis of adaptation should no longer be used in an attempt to explain adaptation to exercise. Authors outline several flaws of this hypothesis, including 1. Supercompensation happens with glycogen, but not with most other systems, such as mitochondria, capillaries, or neurons. The supercompensation hypothesis is a time course and not a mechanism. Right? Supercompensation never said anything about what was happening, just said this is the pattern we're observing. 3. The supercompensation hypothesis implies that recovery is essential for adaptation, yet the heart adapts to exercise despite continuous contraction. Now, I don't know if the heart is necessarily a good comparison, cardiac muscle, but the point is kind of made, right? We know that people kind of can train fairly continuously and they'll keep adapting, as long as the load isn't too heavy. 4. There is little actual evidence that the supercompensation is essential for adaptation, and that's really the key. When they're doing measurements, you're not seeing a decrease in muscle mass with training. You may see markers of muscle breakdown, but that's for recovery and repair, right? You don't train and come out with less muscle, and then suddenly a week later you've got a little bit more. It doesn't work that way. They add, alternatively, it has been suggested that the signal transduction hypothesis of adaptation is more appropriate for explaining adaptations. The hypothesis suggests that sensor proteins respond to exercise signals, working through various pathways to regulate gene, protein synthesis breakdown, and other adaptive responses. Unlike the general adaptation and the supercompensation hypothesis of adaptation, this hypothesis explains how adaptations occur and is supported by what happens in a human model following exercise, right? Not only is the supercompensation model it's not seen in molecular studies of exercise. It's not. You don't see a decrease in mitochondria with endurance training. You don't see a decrease in capillary number. You don't see a decrease in muscle mass. But over time, you see an increase in mitochondrial number, an increase in capillary density and number, and an increase in muscle mass. And that's being performed by adaptation, gene expression, protein synthesis. It's not through supercompensation, and the General Adaptation Syndrome is not a good model of it unless you're killing your athletes. And like I said, they tend not to perform well, although they'd probably be lean enough for modern physique standards. So that's basically it. The supercompensation model needs to go the way of the dodo. It contextually applies for glycogen, but you don't see stair-stepping up levels. It doesn't apply to any other system in the body. Adaptation over time is a much better thing. I guess this is as good of a time as any to talk about a question that came up in my Facebook group. And it has to do with my specialization cycles. And the way they're basically laid out is for roughly 4, maybe 6 weeks, more like 4. You just beat up on a couple of muscles. You just absolutely train the absolute shit out of them. And I've pointed out that in Then for 2 weeks, you reduce the volume immensely. And I've pointed out that you frequently see continued growth during those 2 weeks. And someone asks, isn't that supercompensation? Well, no, it's not. I might call it overcompensation, like guys who drive big trucks. Usually I call it the long-term delayed growth effect, which will only make sense if you're at super training. But it's not, because again, supercompensation suggests that you are depleting something and then rebounding to a higher level. That's not what's happening in my specialization cycles. At no point are you weaker. At no point are you smaller throughout the cycle. I think it reflects one of a few things. One, it could just be glycogen in water being stored. It could be the fact that people forget adaptation is long-term, right? Protein synthesis does not turn off instantaneously. Repair of tissue does not turn off instantaneously. And by maintaining that intensity at a lower volume, you basically just continue growing. But it's not supercompensation. It is simply a continued adaptation. Fitness fatigue is a descriptor of the actual performance more than the adaptations in the muscle or the system. The curve looks very similar, but it describes something more nuanced and something more accurate. It is a modeling system, but it doesn't tell you what the adaptations actually are. We know that adaptations are occurring through increased gene expression, mTOR, as I talked about in my tension series, protein synthesis, and breakdown, make no mistake, and other adaptive responses. Over time, those signals stimulate adaptation. But at no time do you see a decrease in any of those physiological tissues that then rebound to a higher level. Because supercompensation is just, not only is it not an accurate model, it's wrong. It's not how any of this works. And training systems based around that idea are equally out of date. Fitness fatigue is a much better model and leads us to a completely different conceptualization of the training process. And the General Adaptation Syndrome appears to have nothing to do with any of this.